In this video, we will look at several examples of hypothesis tests for a mean or an average. So remember the 5 basic steps of a hypothesis testing procedure. We start by stating our null and alternative hypothesis, statements about population parameters. So in this case, about the mean. So our null hypothesis will be a statement about the mean equaling something, and the alternative will be the mean is less than or not equal to or greater than. We then use the sample data to calculate a test statistic. We will then look that value up in a table to get our p-value and then determine our result. Do we reject or fail to reject H0? And then always remember in any hypothesis test to state your conclusion in the context of a problem. So we'll look at 2 cases for a mean. Much like we had with confidence intervals, we have case 1 where we assume the standard deviation is known, the population standard deviation, sigma, is known. In that case, we will have a z-test, much like we had a z-confidence interval. Also remember, case 1 is sort of the unrealistic case. Oftentimes, we don't know the standard deviation. Case 2 then is a t-test, basically the same hypothesis test, only we'll use the t-table instead of the z-table. So here's a summary of the z-test. Notice we have a random sample. We're going to calculate x bar from our random sample, and here we're assuming sigma is known. So we start with the null and alternative hypothesis. Then we will determine the test statistic. And notice here, the idea is we're comparing the hypothesized value of the mean with the sample. Notice mu here in this formula is the value of the mean in the null hypothesis. It's the initial claim or the starting point. Then x bar is our sample mean. So if you think about it, if x bar is really close to the mean, then the z value will be close to 0, indicating that the mean tends to, or that the sample data tends to agree with the null hypothesis. So as the z values get bigger and bigger and bigger, that's more and more evidence to reject H0 or to contradict H0. After we calculate the test statistic, we will look that value up in the table and get a p-value. And then we'll draw our conclusion, reject or fail to reject based on our p-value. And so again, the smaller your p-value, the more evidence you have against H0. So small p-values lead to rejecting H0. And then the last step is put it back in the context of the problem. So an example for testing a mean with sigma assumed to be known. Suppose we look at cholesterol levels for only children. So the average cholesterol level for American adults is 190. So we take a sample of 35 adults who are only children and found the cholesterol level to be 198.2. Now if we assume the standard deviation is known to be 15, so sigma equals 15 here, do only children have higher cholesterol? So we'll test with alpha as 0.05. So we go through our steps. Our null is the mean is 190. That's what we know. The average for all American adults is 190. The question is, for our group of only children, is that mean higher than 190? We'll use alpha as 0.05. So we plug into that z test statistic. Notice I take x bar minus the mean all over the standard deviation divided by the square root of n. Plug all that in, I get 3.23. So the p-value, remember, you take that test statistic and look it up in the table. And you're looking for the probability of being more extreme than your test statistic. So if I look more extreme than 3.23, means further out in the tails. So if I look at the probability of a z-value greater than 3.23, I get 0.0006. Because remember, when you look it up in the table, you actually get 99.94. Remember that z-table always gives you lower tail, so if I want upper tail, I go 1 minus that. So my p-value is really small, so that should lead me to reject H0. It is smaller than alpha. 0.0006 is obviously less than 0.05. So my conclusion here, remember when we reject, we're drawing a sort of definitive conclusion. We're making a statement against H0. We're saying we have strong evidence to reject H0 and conclude, in this case, that the mean cholesterol level for only children is higher than the average for all Americans. Now if we look at a t-test example, this is basically the same test. We still have a random sample. We're going to calculate x bar from our sample of size n. But here we're not assuming anything about standard deviation. We're going to calculate the sample standard deviation from our data. So we have the same 5 steps. We're going to have our null and alternative hypothesis. We're going to calculate a test statistic. And notice it's exactly the same. It's just we've got sample standard deviation instead of assumed population standard deviation. But it's still the same idea. If this t-value is close to 0, that tends to tell us that our data and the null hypothesis tend to agree with each other. So we'd fail to reject. But as the x bar value gets much different than that hypothesized mean, this t-value will get larger either way, to the negative side or the positive side. So the further it is out, the larger the t-value, the more evidence we have against H0. And so again, a small p-value would lead us to reject H0, and then always put your answer back in the context of the problem. So if we look at an example for a test of a mean with sigma unknown, so a t-test here. So suppose a professor wants to determine if review sessions help exam performance. So he samples 15 students who attended a review session, and their average exam score was 76.8, with sample standard deviation 8.23. Now suppose from previous semesters the instructor went back and looked at average exam scores in previous semesters and the average was 74. Is there evidence review sessions significantly improve exam scores? So if we think about our first step, from previous experience we knew the average was 74. That was kind of our starting point. So let's assume that the mean scores on these tests is 74. Now if we want to determine whether these are effective, these review sessions, we'd like to see the mean increase. So is the mean greater than 74 would be our alternative. In this case, we'll use alpha's 01. So the test statistic, I take x bar minus the mean all over s divided by the square root of n. If I plug all those numbers in, I get 1.32. So now I need to go to the t-table here and look up 1.32. Now, with the z-table, you can look up a z-value and get the exact probability of being less than or greater than that. The t-table is a little different. So let's look at the t-table. So I want the probability of t greater than 1.32. So remember with the t-table, the first thing I need is my degrees of freedom. I had a sample of 15, so sample size minus 1, I'm looking at 14 degrees of freedom. So across that row down there at the bottom of the table. So now I'm looking at a one-tail area here, greater than 1.32. So if I go across that row at 14, where do I find 1.32? Well, it's not in the table exactly, but I can see it's somewhere between 1.2 and 1.34. So 1.2 corresponds to a one-tail area of 0.125, 1.345 corresponds to a right tail of 0.10. So 1.32 would have a tail area somewhere in between there. So from the table I could conclude that the p-value is somewhere between 0.100 and 0.125. Notice I can't find the t-value exactly in the table. Now there are other resources where you can find the p-value exactly. There's a website, stattrek.com, that has a lot of statistics calculators. If you go to stattrek.com, down the left side, you can look up normal distribution, binomial distribution, t-distribution, all sorts of different things. So if you do that and plug in 14 degrees of freedom and a t-value of 1.32, you can get the exact p-value. And notice that 0.1040 is between 0.1 and 0.125. Also, if you have a TI-83 or 84 calculator, there's a T-CDF, a T-PDF. Those functions, you can put in a lower limit, an upper limit, and then your degrees of freedom. And for that upper limit, you just need to put in a really big number. Or if you can find the infinity key on your button, you could go 1.32 to infinity. So there are multiple ways to get the exact value for a t-distribution p-value. But if you're using the table, we can just kind of approximate it. So if we go back to our example here, our p-value is 1040. So now the next step is, what is our conclusion? Well, notice here the p-value is bigger than alpha. 0.104 is bigger than 0.01. So we fail to reject. So remember, when we fail to reject, we sort of have the inconclusive conclusion. In other words, we don't have strong evidence to contradict the null hypothesis. So as far as we know, we can't conclude that these review sessions significantly improve exam scores. Now you'll notice here that the average was slightly higher. But remember, with a hypothesis test, we have to account for standard deviation or variation. We have to account for sample size. And so that's not enough higher than 74 for us to conclusively say that review sessions are improving exam performance. So there's your 5 steps for a hypothesis test on a mean. So tests on a mean, if you assume standard deviation is known, you can do a z-test and do your 5 steps. If sigma is unknown and you have sample standard deviation, it's basically the same 5 steps, you're just using a t-distribution.